Swayam Prabha. Digital India. Educated India.
Welcome to the course on advanced machining processes. Today I am going to discuss about electric discharge micro machining process. Organization of the today's talk is introduction, then working principle of electric discharge micro machining. After that I will tell you the process parameters of the process, then applications of the process. Introduction. We have already seen in the lecture on electric discharge machining, and this is the lower scale version of electric discharge machining. So, let us see what are the common issues related to micro machining. First one is the scaling effect on the process mechanism, material morphology, what kind of material you are going to get and after electric discharge micro machining. Then mechanical, electrical, electron compatibility. After that I am going to discuss about the process material interaction, removal of material in the form of debris, rather than writing it here my chips, it is the one we normally call is debris, not the chips, lubrication, curing, etc., tool and little bit of equipment design. After that we will show you a actual real life demonstration of the electric discharge micro machining machine that we have at IIT Kanpur. Now, what is electric discharge micro machining setup elements? It is the same as you can see what we had in electric discharge machining, that is the tool which is also known as cathode and made of electrically conducting material. Then you have the workpiece, again made of electrically conducting material. The workpiece material should have a certain minimum conductivity, then only you can use this electric discharge micro machining process. And then for filling up the gap between the tool and the workpiece we use the dielectric, and there are various kind of dielectrics which I will tell you, and to make them electrically conducting the whole circuit we have power supply. And the working principle is very simple, you can see clearly here. There is a servo control of the tool, then there is a tool, dielectric is there, workpiece is there, and the gap is filled with the help of the dielectric. When the potential gradient between the cathode and the anode, that is the tool and workpiece, is sufficient enough to break down the dielectric, then you get what is known as spark. In this process we are not interested in the arc, so we are always interested in the spark, so people call it as electro spark machining. In the beginning it was mentioned like electro spark machining when EDM was developed by Lazarenko brothers, and the working principle is the same as that of electric discharge machining. So, I am not going to discuss much about the details of this process. Many of the elements of micro EDM process are the same as that of EDM. However, we have a comparison table over here. As you can see, the macro EDM, where the size of the parts or the features that you are creating is bigger than 1 millimeter, while in case of electric discharge micro machining or micro EDM, size range between or below than or less than 1000 micrometer. In case of macro EDM, material removal is higher compared to material removal rate in case of micro EDM. Then higher spark gap, the gap between the tool and workpiece is normally larger, potential applied is also larger. So, the spark gap is also larger in macro EDM as compared to micro EDM. Power consumption in the process is high definitely in case of macro EDM compared to micro EDM. Higher discharge voltage used, approximately greater than 80 volt in case of macro EDM, while it is just 20 volts or less than 20 volts in case of micro EDM. So, one thing should be very clear, that the size of the spark in case of micro EDM is going to be much smaller than size of the spark in case of macro EDM. Or in other words, we can say that the crater size that you are going to obtain in case of micro EDM is again going to be smaller than, much smaller than macro EDM, because energy per spark is much smaller in case of micro EDM as compared to macro EDM, and that is simply means that you can get much better accuracy in case of micro EDM as compared to macro EDM. And DC or very low frequency pulsating discharge current is applied in case of macro EDM, while very high frequency of pulsating discharge current is applied, and T on time can be as small as 1 microsecond. So, we can clearly see there is a basically a scaling down or scaling difference between macro EDM and micro EDM. Let us again reiterate in brief the working principle of electric discharge micro machining. I am saying reiterating deliberately because this principle is the same as the principle of EDM, and I have already discussed EDM principle, working principle. Now, spark machining, this was, as I mentioned few minutes back, it was initially named as electro spark machining by Lec30 brothers. So, again we can say spark machining method is the same as the electric discharge machining method. It is used for cutting complex or odd shapes in hardened materials that are electrically conductive, and one more thing, that it can machine very hard materials if it is electrically conducting, or you can say difficult to machine materials can be easily machined by this particular process. Here you connect the electrode, that is the tool, and workpiece to the negative and positive terminal of power supply, as we have seen in the schematic diagram in the earlier slide, and these electrodes, that is the tool and workpiece, are brought closer to each other, and the gap between the two is few microns, as I mentioned in the earlier slide, that the working gap is few microns, while in case of EDM it is much larger. And tool is negatively charged, that is the cathode, and workpiece is positively charged as the, and it is called as anode. However, in certain cases you may have to use the reverse polarity, but not much research has gone into that. So, I am not commenting much about that particular feature of the electric discharge micro machining. As the two conductors get close enough, a spark will be produced across the dielectric. That means the when potential gradient in the path of the dielectric, that is there between the anode and cathode, becomes so large that it breaks down the dielectric, then you have what is known as spark. Spark has a localized high intense energy, heat energy, and this energy is good enough to melt and or vaporize the workpiece material. Once melting has taken place, then dielectric will eject out the molten material from the cavity, or if vaporization takes place, then due to the sudden explosion due to the sparking taking place or plasma formation, that shock wave is generated, and that shock wave will remove the molten material from the cavity, and as a result a small amount of material from the tool and workpiece both is removed. That means here one has to note again that in case of EDM, here also wear of the tool as well as wear of the workpiece material both is taking place, but definitely wear on the cathode, that is the tool, is less compared to the wear on the workpiece, that is the anode. Here you can clearly see how the spark evolution takes place. Here is the tool, that is cathode, workpiece, and dielectric is over there. And in the initial phase of sparking, vapor bubble is there and it avalanches, and you can see the avalanche growth takes place, plasma formation takes place, and full plasma formation is there between the cathode and the anode. And this plasma has intense heat energy, which is responsible for removal of the material from the workpiece as well as from the tool at the same time. That is why wear of the tool as well as wear of the workpiece take place. Now those craters are shown over here in the last figure. There is a smaller crater at the cathode and larger crater at the anode. This indicates that more amount of material is removed from the workpiece and less amount of material is removed from the tool. However, theoretically we want that the removal of the material from the tool should be 0, if not 0, as low as possible, so that degeneration of the shape of the tool does not take place. Process parameters. Here you have a fishbone diagram of the process parameters. We have already seen that dielectric fluid is there, then oxidization stability and flash point of the dielectric fluid play an important role. Dielectric strength is there, which will decide the voltage required for breakdown of the dielectric, and the viscosity of the dielectric is also important because it determines the flowability of the dielectric, and especially in case of complicated shapes, the dielectric should flow in all inaccessible areas of fine fissures, so that sparking will take place over there and you get proper machining. Then there is a tool material. Tool material should have easy machinability, so that you can give complicated or any desired shape to the tool, because what you are going to get on the workpiece is the replica of the tool, very close to the replica. I do not say exactly the replica. And tool material should definitely be electrically conductive. Melting point of the tool material should be as high as possible, so that the wear of the tool is minimum, and it is also the function of thermal conductivity that will decide the temperature of the tool, and definitely tool material should have low wear rate. And then you have the machining parameters, voltage and current, they will decide the spark energy, and that spark energy will decide the size of the crater to be formed on the tool as well as on the workpiece. Then frequency of sparking is another very important parameter. It will affect accuracy in surface features or morphology that you are going to get after machining. And then duty cycle, that is nothing but T on, that is the on time of the pulse, divided by T on, that is the on time plus off time of the pulse, that decides the duty cycle. And this plays an important role in case of EDM as well as electric discharge micro machining. The output of the process are measured, or the performance of the process can be measured in terms of machining rate, dimensional accuracy that you are getting, and surface integrity, that is again very important parameter that will decide the surface finish, the micro cracks, if any, on the surface that has been machined, and morphology or texture of the surface again plays an important role. And how much is the recast layer, how much is the surface damage, I am not going to discuss them, but these are all the features that we have seen while we were discussing the electric discharge machining. There I have told you in detail about the heat affected zone, that is HEA, Z, recast layer and other features. You can perform various kind of the operation using the EDM process. You can do micro milling operation, as you can see here. Here is the micro milling tool or cutter, and you can see here micro milling operation is being performed, the feature is being created with the help of the micro tool. These are enlarged view of this figure, and then you can have different kind of the tools, as you can see on the top right hand side figure. And then here is the titanium NSM clip was machined on a S4 axis milling. This milling machine is the 4 axis milling machine. Then you have a mechanical micro drilling technique developed by Hitachi via mechanics enables the formation of 10,000 100 micrometer diameter through holes on a 0.5 millimeter thick wafer. You can see the kind of the holes that have been developed, thousands in number formed, and with and the diameter of these holes is 100 micrometer diameter, and the thickness of the wafer is 0.5 millimeter. So, this is very useful for fine hole drilling in large quantity. Again, note that there is no physical contact between the tool and the workpiece. So, mechanical forces are not working either on the tool or on the workpiece, and tool is fixed in spindle and rotated, and workpiece is fixed on the fixture. You can see here the tool is fixed in the spindle and this rotates, and workpiece is fixed in the fixture, and sparking is taking place. So, you have the uniform hole or uniform milling taking place over there. You are giving x and y motion to the workpiece, so that you can create these kind of the features as shown by arrow over here. Motion of tool is controlled by 4-axis CNC control of the machines. It uses drill bit of various sizes below 100 microns. You can see here on the top right hand side figure, various sizes of the drill bits are shown over there, and these are all micron size tip. It does not involve anyway. These tools can be made by the EDM process also, and you can perform the mechanical cutting. When you are performing mechanical cutting over here, then cutting forces are there. You can perform the machining process, fast machining process. Surface, when you are doing mechanical machining, then definitely it will consist of burrs, and it is not suitable for high aspect ratio holes and features, because the probability of breakage of the tool is high. You can prepare micro EDM electrodes. Properties of the micro EDM electrode: it should have high electrical conductivity, high thermal conductivity, high melting point. It should be less expensive, and manufacturability should be easy, so that you can make the electrodes of different shape and sizes. Electrode type and material are given here. You can have the metallic electrode, where you can use copper, tungsten, brass, etc., various kind of the materials. Then you can have non-metallic electrode like made of graphite. Please note that graphite is electrically conducting material. Combined metallic and non-metallic like copper and graphite, you can have the electrode made of these materials. Metallic coating on insulator can be made, so that you can use that insulator tool as a micro tool in micro EDM process, because you have the coating on the outer periphery which will work as a conducting material, electrically conducting material. So, you have copper on molded plastic and copper on ceramics. These tools can also be used for electric discharge micro machining, and then you can make the tool with the help of the powder metallurgy, PM. Powder sintered fully or partially, or green compact can be used as the tool. There are various kind of the tool materials, as I have just mentioned, and they have certain properties as I have elaborated over here. Like graphite, it has good machinability, wear resistance is high, resistance to high temperature hours is also high, and very low current densities, and it can be used on all metals. Copper is very commonly used tool material, and it has oxidation resistance, better wear resistance than brass, and difficult to machine than either brass or graphite. That is one of the weakness of this particular material as the micro tool for EDM process. Again, it can be used for all kind of materials. Then brass, it is used to form EDM wire and small tubular electrodes, and again this can be used in combination with all other materials. Then there is tungsten. It has very high melting point, just like 3410 degrees centigrade. It has high resistance to arcs and low conductivity, and it is used where small holes are to be drilled, because it is much stronger than copper and brass, so that it can resist even mechanical forces and definitely it can resist high thermal load because its melting point is 3400 degrees centigrade like that. Copper tungsten again used as composites of tungsten and copper, making deep slots under poor flushing conditions and high accuracy work. Then you can have a combination of copper graphite, it's composites of copper and graphite, and again it can be used for all metals. This way you can see these are the various kind of the materials which are used for making the tool or the electrode, and they are the same as you use in case of macro EDM process. Then there are various kind of the dielectric which are used in micro EDM, like mineral oil which has low viscosity, and then roughing application with heavy oils is efficient. White oil or kerosene is very commonly used in the past, it was very commonly used in the past. It has very low viscosity, so that it can easily reach to the complex geometry area or features. For finishing and super finishing purposes, it is commonly used. You can use tungsten carbide when short duration charges are required, when you are using the tungsten carbide. Water, again you can use deionized water as dielectric, and viscosity is very low, and it is reserved for micro machining and wire cutting. This is very important to note that water, deionized water, is invariably used for electric discharge, wire cutting, and also mostly used for electric discharge micro machining. Naphthic oil can also be used. It has high flushing with high accuracy and surface finish. Air is also being used as the dielectric in macro EDM as well as in some cases of micro EDM. Power supply, normally in electric discharge micro machining, basic RC circuit power circuit is used in the power supply, and transistor control circuits are normally used for macro EDM. But please note that initially it was only the RC circuit which were used in EDM process, but later on researchers developed transistor controlled power supply, and nowadays in EDM most of the cases you are using transistor controlled circuit for power supply. Again, workpiece material should be electrically conducting, and all kind of workpieces materials which are electrically conducting, they are listed here. You can use them like aluminum, cobalt, tantalum, titanium, tungsten, vanadium, inconel alloy, astolloy, baspalloy, carbide, PCD, polycrystalline diamond or cubic boron nitride, that is a PCD or CBN, graphite, then copper, metallic electrodes are used for the copper also, and all grades of stainless steel and tool. Now the basic requirement here is, as I have mentioned here at the top, is that they should be electrically conducting, so you can use them either for workpiece making the for making the tool, or as a workpiece depending upon the designer. Now there are some specific applications of this particular process. Now you can see here that 6.5 millimeter diameter hole is machined in the 50 micrometer stainless steel plate, and you can see the diameter 6.5 over here, 8.5 micrometer diameter, 10.5 micrometer and 12.5 micrometer. Now 2.5 millimeter valve separating 12 micrometer slot is there. This is the 2.5 millimeter valve, and this is the slot which size is 12.5 micrometer. Then here is a micro turbine in steel. This was prepared with 3-dimensional EDM process. You can create the microfluidic channels in stainless steel as shown over here, and here is the scale, that is the 100 micrometer. So you can see the size of the microfluidic channel. Now this is one of the very small size electrode that can be used for micro EDM applications, and its size is 2.54 micrometer, as you can see there. Now here you can see the micro holes that have been drilled. The size of the micro holes is just 13 micron, and you can see the enlarged view of the holes as well as the workpiece. Now here you can see the internal gear that has been made, and this is the scale. Now you can see SEM picture showing the swirling action and the milling marks. These marks are generated during machining due to rotation and forward feeding of the tool. Again, machine channel is there. These are the SEM pictures. Now this is micro turning, with the help of which a tool is being prepared, and this tool can be used for electric discharge micro machining purposes. 22 micrometer electrode fabricated by micro turning process. Here tool is fabricated by the conventional micro turning, and this tool can be used for the purpose of electric discharge micro drilling operation. Again here 44.5 micrometer copper tungsten electrode is fabricated by block electric discharge grinding process. This here it is fabricated by electric discharge grinding. Again this is also fabricated by block discharge electro discharge grinding process, and the tool diameter is 45 micrometer. So these tools can be used for electric discharge micro milling operation also. They can be prepared by BEDG process or micro turning process, and then can be used for electric discharge micro machining or micro drilling purposes. Now you can see BEDG process that is performed, and some of the work has been done at IIT Kanpur. So you can see here is the tool which is being made, and this is the sacrificial electrode. What you can do, you can keep rotating it, the tool, and bring this tool very close to the workpiece over here, that is sacrificial electrode. So because of sparking, the material will be removed from the tool as well as the workpiece. Now since the diameter is continuously reducing of the tool and it is rotating, so that you will get finally a proper diameter tool made over here. However, this is a scrap kind of the piece that is named as sacrificial electrode, which is used, which is electrically conducting, and it is used to create the sparking between the tool as well as the workpiece. So here this tool, which we are calling as the tool, is working as the anode, and this is working as the cathode. In the same way, you can prepare the step tool. You can see different steps have been created on the with the similar process. Now here you can see the time required and volume removed from the workpiece material. If you have low energy level, say 50 joules, 60 microjoules, 72 microjoules, then definitely it is going to take very long time to make the same feature. If it is the high energy level, 500 microjoule, 720 microjoule, 2000 microjoule, then definitely it is going to take much lesser time to remove a certain amount of material that is given here on the FC saw. So this is the kind of the taper that you can produce while you are drilling the hole, micro drilling the hole, with different kind of the energy level of the sparks that is shown over here, and this is the taper that you are going to get. Now this is a conventional turning with the help of which you can prepare the micro tools, as you can see in 4 different phases. This is the micro tool that is being prepared, and later on these tools can be used for electric discharge micro drilling operation. Now this is the electric discharge micro machining, or rather I should say micro machining machine, that is available at IIT Kanpur, and its name is DT110. Now micro turning operation you can perform on this particular machine itself, and that figure is shown over here. Then you can use the same machine for conventional micro milling purposes. Tool is here, and this is the workpiece and this particular one, and then you can do the milling operation over there. Here is on machine measurement can be done. Then you can see micro EDM process being performed over there. Here you can do the micro wire EDM process, and wire is running around, and you can see, and that is cutting the workpiece into the desired shape. And then micro wire EDG, electric discharge grinding operation, is shown over there. Thank you very much. Now Mr. Karthikeyan will give you the demonstration of the electric micro machining machine, which has the features as I have shown to you in the last slide, that it can do conventional micro turning, conventional micro milling, and then it can do the electric discharge micro machining. It can also do the electrochemical micro machining operation, which I have not shown there. Thank you very much.
Welcome. I will demonstrate the micro machining facility at IIT Kanpur. The machine is DT110 micro tool, which is capable of performing various operations, which includes both conventional and non-conventional. In conventional operations, processes such as micro turning, micro drilling, micro milling can be performed. In non-conventional operations, processes such as micro EDM, micro wire EDM, micro EDG and micro wire EDG, block EDG can be performed. I will demonstrate the various features of the machine now. The machine has two tables. One is horizontal table, another one is vertical table. The availability of two tables makes the machine more flexible. The machine has 4 axes of motions. The axes are y-axis, x-axis, z-axis and the rotational axis. The direction of convention for all 3 axes is shown in the schematic diagram. Even though all the 3 axes are shown on a single table, it is not so in the real machine. In the machine, the horizontal table is controlled by y-axis, whereas the vertical table contains x-axis and z-axis as well as the rotational axis. The axis of travel for each axis is as follows. The x-axis can travel to a maximum distance of 200 mm. The y-axis as well as the z-axis can travel a distance of 100 mm. The accuracy of the 3 axes is plus or minus 1 micrometer upon 100 mm. The resolution is 0.1 micrometer for all 3 axes. The repeatability is 1 micrometer for all 3 axes. The 4th axis of motion is rotational motion. The rotational motion is performed by a servo motor. The servo motor can rotate the spindle either in clockwise direction or anti-clockwise direction. The speed of the spindle can be varied from 1 rpm to 5000 rpm. During EDM process, since one of the electrode has to be electrical conductive, the spindle is electrically isolated from the machine body. For EDM process, 2 elements are very much essential. One is the power supply, another one is the dielectric. For power supply, the machine has 230 volts input supply with 50 Hz frequency. For the feasibility and easy accessing of the electrodes to the power supply, a power board is kept closer to the table. This power board contains a port for EDM, port for wire EDM, port for spindle, port for touch probe and port for OMM. The other element of EDM is dielectric. The machine has very good dielectric circulation system. The dielectric from the tank through the pump filtered and enters to the nozzle through a regulator. The regulator controls the pressure of the dielectric fluid. The fluid from the pump goes via the regulator to the nozzle to the tank. The regulator controls the pressure of the fluid. The fluid as enters into the tank will get filled in the tank till a certain level is reached. Once the level is reached, the dielectric overflows through this valve to the another tank which contains a filter. All the debris which are formed during the process is filtered in this filter, and the filter dielectric will enter into the tank which is under the table. In this way, the dielectric is recirculated continuously during the process, ensuring fresh dielectric for the process. Now I will demonstrate the control panel of the machine. This portion of the control panel is a display part which shows the machine coordinate, the work coordinate, the speed setting and the machine setting. The machine coordinate refers to the machine origin point, that is machine world coordinate system. The work coordinate refers to the origin point on the work surface. The other side of the control panel contains various switches which operates various parts of the machine. The first part is called homing. This is used to initiate the machine. When the machine is switched on, the homing operation is performed so that the machine works without any error. This operation is called jog mode. This is used to move a particular axis in either positive direction or negative direction to a specific value. 6 different specific values are available for jog mode. The third switch is MPG. This is manual pulse generator. The manual pulse generator will operate by a device which is interfaced with a controller. The device is as shown here. The fourth command in the front panel has 6 options. All these are 6 different switches which perform 6 different operations. These 3 options are used to change the value of speed or feed or EDM feed during operations. That is, during execution of program, the speed or the feed or EDM can be varied with certain percentage. The next window is MDI. MDI is manual data input. This window will help the user to execute an individual block of command. The third window is auto. This is the window where the program is executed. Here there are 4 options given for the user. To open a new file, this is to open a file which is already available in the library. It is to save a file. It is again another option for saving a file in different name. The next window is WCS. WCS refers to World Coordinate System. In this machine, there is a feasibility for having 6 different origins on the workpiece. So the origins can be G54 to G59. Each G code will have a corresponding point which is called P1. So G54 is called by P1, G55 is called by P2, G56 is called by P3 and so on, and G59 is called by P6. So by calling these points, the present point will be converted into an origin which is of 6 different values. So by this, user can set 6 origin on the workpiece surface, and these origin can be called during the program. The next window is EDM, ECM. This window will help to set the parameters used for the process. In EDM, as it is well known, for an RC circuit, the parameters are voltage, capacitor, polarity and threshold. The gap voltage can be varied from 80 volts to 140 volts. The capacitance has 5 different values, which can be 10 picofarad, 0.1 nanofarad, 1 nanofarad, 10 nanofarad, 0.1 microfarad, 0.4 microfarad. 5 different values of parameters can be set simultaneously and called in the program. These are represented by M codes, which are M211, M212, M213, M214, M215. The next option is OMM. online machine measurement option. Using this window, the camera can be interfaced to the controller. Whatever the image recorded by the camera can be seen in this window. The last option is, this is to set wire EDM parameters. The parameters are the speed and the tension. The another box available is for coolant. Here the dielectric is chosen for the process. So these are the various features of the control panel of this machine. Now I will demonstrate an example of a program. Open. This program is used for making a slot in conventional milling process. The command starts with G90. G90 refers to absolute mode. G10, P1, X0, Y0, Z0, G54. This command is used to set the present position of the tool as the origin point. G00 shows the rapid transverse motion. Through G00, Z is lifted by 5 mm from the origin. M03 S2000 is to rotate the tool with 2000 rpm in clockwise direction. G00 Z0 will bring the tool back to the 0 position in a rapid transverse mode. G31 Z-10.0 F3.0 is a touch probe command. In this command, the tool moves down to a maximum of -10 mm till it touches the workpiece surface. When this tool touches the workpiece surface, due to short circuiting, the motion stops. This senses the 0 point on the workpiece surface. G00 is at 0.5. It lifts the tool back to 0.5 mm in rapid mode. G01 is at -0.5 F5. This is a linear interpolation motion where the tool moves down by a distance of 0.5 mm in downward direction. G01 is at -0.5 F5. This is linear interpolation in Z axis, which makes a tool to move a depth of 0.5 mm. G01 X20. This is again a linear interpolation in X axis direction. This makes a tool to cut the workpiece along the distance of 20 mm in X axis. G00 Z5 is a rapid transverse mode where the tool is lifted to 5 mm from the origin. M05, which will switch off the spindle motion and the program. So these are the blocks by which a program is executed in any process. Now I will demonstrate the various processes which can be performed in this machine by explaining the attachments. The first process which I am going to explain is micro turning. Micro turning has a single point cutting tool and the tool post. In micro turning, the tool is fixed in the tool post like this. These are the screws which holds the tool, and the tool tip portion is upward. It should be fixed such a way that 50 mm of the tool should be outside this and the cutting zone should be kept closer. The fixture and the tool is assembled on the machine horizontal table like this. In this operation, the workpiece is fixed in the spindle and the tool is clamped on the table. The workpiece rotates and it is given with the feed motion, whereas the tool is provided only with depth of cut. This is slightly different from the conventional machine where the feed as well as the depth of cut is given on the tool. This diagram shows the turning process during machining in the micro tool machine. The next process is micro milling or micro drilling. In both the process, the workpiece is fixed on the fixture. This is the fixture. The tool is held in the spindle via a collet. These are 100 micrometer cutting tools for milling or drilling operation. The schematic diagram for the milling process is as shown. Here, this is the spindle which contains the milling cutter. The workpiece is fixed on the fixture which is shown before. The tool is rotated and the operation, the X, Y, Z motion is being performed through the program. This is a spindle collet holder. The tool is attached to a spindle by means of a collet. The collet and the collet holder assembly are two which helps in holding the tool to a spindle. The collets are available of different sizes based on the size of the shank portion of the tool. The next process is wire EDM. This is the setup for wire EDM process. This shows the wire which is used for the wire EDM process. This is the fresh wire and this is the used wire. This is the fixture which is used to clamp the workpiece. The workpiece will be a thin plate and it is clamped by means of a screw or a magnet between these 2 points, so that the wire can easily travel in this area without touching the fixture. Now I will demonstrate how the wire is connected to the fixture here. The schematic diagram for wire EDM process is as shown. Here, this is the position where the spool is fixed. These are 2 mid rolls. This is another guide roller. This is the tensioner. These are 4 guide rolls, and this is a portion where the provision is given for the wire to freely move in contact with the workpiece. This is the take-up roll. This wire EDM setup is fixed on the vertical table of the machine. Once it is fixed, these 4 steps are used to connect the wire from the spool to the take-up roll. The steps are visibly seen in the figure. So through the mid rolls, then the tensioners, then wire comes like this to the bottom portion and it passes like this to the take-up roll. Now this wire is freshly available to be in contact with the workpiece. This diagram shows the contact between the workpiece and the tool. So this wire EDM setup will has a wire which is continuously moving from the spool to the take-up roll, and the workpiece is contained in the fixture. So the wire comes in contact with the workpiece edge and the required profile is being cut on the workpiece. For wire EDM process, either the wire can start from the edge of the workpiece or a predefined hole is required on the workpiece so that the wire can be inserted into that hole and process can start from that hole. In this way, either a profile can be cut from the edge of the workpiece or from any center point of the workpiece. The next process is wire EDG. This process is basically used to cut the tool. It is like a turning process. The setup for wire EDG is as shown. A schematic diagram of wire EDG setup is shown now. Here, this is the feed roll, this is the take-up roll. The wire from the feed roll is passed via tensioner through the wire guide to the main guide, and again it is passed through another wire guide to the take-up roll. This port is to connect the wire EDG setup to the power supply. The wire EDG setup is fixed on the horizontal table, which is different from the wire EDM setup. Here, the wire EDG setup is fixed such that a part of the setup is outside the tank and the part of a setup is inside the tank. That is, the portion where the machining is going to take place is submerged inside the tank, and the portion where the motor is there to guide the rollers is away from the tank. The process happens such a way like this. The tool, which is now the workpiece, is fixed on the spindle and rotated. Now the objective of the process is to reduce the diameter of the tool. To reduce the diameter, the tool comes in contact with the wire electrically. Same as EDM process, the tool material is removed and thus the tool is turned to a specific diameter. Through this process, diameter of tool as small as 2 micrometer can be generated. This diagram shows the major wire guide. The initial diameter of a tool should be lesser than this curve, which is approximately 4 mm. So any tool of initial diameter of 4 mm can be reduced to a diameter of 2 micrometer by wire EDG process. The next process is block EDG. This process is again used to turn the tool. The disadvantage of the previous process, that is wire EDG process, is it consumes lot of time and the wire once used cannot be reused. In other case, this block EDG process is much faster. The tool, which is again the workpiece here, is fixed on the spindle and rotated. This is a stationary sacrificial block. The tool is made to rub against the block electrically. It's again an electrical process wherein the tool, which is the workpiece, is positive charge and the block is negative charge. Since positive is cathode, the material is removed from the tool. Thus, the tool diameter is reduced. By this process, from any initial diameter, a diameter of 10 micrometer can be achieved. In block EDG process, either tool can be stationary rubbing against the block or it can be made to vibrate. The advantage of vibrating the block or vibrating the tool is it will reduce the wear on the block. Therefore, the amount of material removed will be directly proportional to the material removed from the tool. The next process which I am going to explain is micro ED milling. In micro ED milling, the tool is fixed on a spindle and rotated. It is negatively charged. The workpiece is clamped on the fixture onto the table. So during machining operation, the cylindrical tool is made to move in along 3 different axes, X, Y, Z. The figure shows a channel machining where the tool is made to move only along Y axis. So by micro ED milling, any complex shape can be generated by a simple cylindrical tool. These are the channels which are fabricated at IIT Kanpur on EN24 material. The tools used for channel formation is shown here. This concludes the various processes which are possible in this machine. The setup shows a block, a workpiece and the tool. Using this setup, the tool can be first turned by using block EDG process and the machine tool can be used in the workpiece for cutting the channels of defined dimension. The tool is rotated, it is moved towards the block now. The spark is initiated. This spark will remove the material from the tool. In block EDG process, as I mentioned earlier, the tool is positive and the block is negative. So the maximum amount of material will remove from the tool. Now, once the tool is ready, it is positioned to the workpiece. Now the polarity of the tool is changed to negative and the workpiece becomes positive. This is the straight polarity. Now the tool of defined diameter is moved towards the workpiece. Now spark has been started. Now the material is removed from the workpiece. This is the advantage of this process. Simultaneously, tool can be prepared from the block and can be used for the workpiece to machine. Now I have shown you a small demonstration of the facility in IIT Kanpur. Through these facilities, various operations can be performed, as I have shown you. Hopes this presentation will give you some information for your future work. Thank you very much.